Hey everybody, all right, we got work energy power. All right, just locking my um, focus lock in there. So work energy power, we're over in a new unit here, right? Topic 3, energy. Does a power company sell power? Ooh, that is a good question. It turns out it's not. They sell energy, which makes sense, and I'll explain that a little bit later on. Now, most time when you talk about energy, you start off talking about work as the definition of kind of how you build up energy. See here, you got to remember with all these things, it's a way like impulse momentum. This is all a way to account for what's going on in a mechanical system, right? We can keep track of momentum in the system, and we can make predictions about how the system's going to behave. So if two objects collide and you know the masses and you know the velocity of one of them initially and the mass velocity of one of them after, you can figure out the velocity of the other one and so on. All right, so we can predict how the system behaves based on these constructions. Construction meaning something that physicists have created to explain the behavior of systems. So conservation of momentum is one of those constructions. Energy is one of those constructions. It's not really a thing, energy per se. It's a way to keep track of what's going on in the system. Like you think of solar energy. Well, what the heck is that? Well, electromagnetic radiation from the sun hits a piece of silicon with impurities in it, and it ejects electrons, giving them essentially kinetic energy, so to speak. And then we can harness that. That makes what we call a potential difference or voltage, which can push current through wires. So the energy itself isn't really a thing. It's a way to keep track of um, the work that can be done. It's a way to keep track of how the capacity of the solar panel to be able to push current through the wire, right? Energy is stored in gasoline, essentially chemical potential energy. Well, what the heck is it? Well, it's the capacity of the gas to be used to produce physical motion or heat or something like that. So energy, remember, it's not necessarily a thing. It's a way to keep track of the system. All right. So just like we put impulse into something by applying a force, we also put energy into something by applying a force. And impulse was the amount of impulse or momentum gained an object gains is force times time. Work's a little bit different. The work, right? So I think of work as change in energy, right? The change in energy of an object. Remember, objects have energy. We keep track of the energy of specific objects. So when we apply a force over some distance, we change the energy state of an object. Typically, we say it's change in kinetic energy. In fact, the work energy theorem is the force multiplied by the distance that equals change in kinetic energy. That's how we write it when we're talking work energy theorem. It's important to note this force should technically be force parallel to the displacement. D is a bad variable. It just is. It really should be parallel to the displacement vector, delta x or delta y, delta z, delta r, whatever. Let me try to explain that a little bit. So, for instance, the classic example is pulling a box with a rope or something, right? Force, we have an angle, right? We slide it over some distance. I will call it D just because that's what the reference table does. Not that that really matters a whole lot at this point. But anyhow, force multiplied by the distance gives us the amount of work. However, this force isn't just pulling this object horizontally, parallel to that distance, right? It would be more efficient, possibly, if there was no friction, to pull this way, straight on. That's what we call the parallel component of the force to the displacement. That's F and then a parallel sign. You know, this component of the force would be the component perpendicular to the displacement. that component is actually helping the helping with the contact force here, the normal force, to overcome gravity. That force would actually reduce the amount of friction. So it kind of becomes, okay, what's the most efficient angle to pull something at if there is friction? Well, that's interesting. We could do some calculation work on that later on if we wanted to figure that out. So when we do this, work equals FD. You got to remember it's the component of the force parallel to the displacement. So really, it's typically F times the cos of theta times the displacement. Something later on, we'll call it a dot product or a scalar product. We're not going to worry about that right now. That's something we talk about in AP Physics C a little bit. So work equals force cos theta times displacement, or FD cos theta. So sometimes you'll see an example about this. There's a nice sample problem on page 81 in the review book showing this, right? So find the x component of the force multiplied by the distance, and you'll note that the units here are newtons times meters, Newton meter, which we call a joule. All right, and Newton meter is a joule. All right, so power then, the review book immediately goes into to define. So I should say right now though, so that joule being work, change in energy is in joules. That means energy has units of joules as well. Now the review book, just to kind of keep in the same order as the review book, because these are review videos that I hope to use later on post-COVID time, power is defined as the amount of work being done per time, or force times distance over time. Then if we look at distance over time, that's like force versus average velocity, another way to calculate power that we didn't really talk about very much. This could also be the slope, right? If we had an energy versus time graph, how's the energy changing as a function of time? The slope of this would be capital P for power. So power, the variable is capital P. Momentum, the unit is lowercase p. That's kind of annoying, but it is what it is. So the units here, the units for power are a joule per second, which is what we define as a watt, or capital W, watt. And you've seen that all over the place. You see watts all over this. Microwaves, light bulbs, radios, charged cell phone chargers, all kinds of things. You see power ratings in watts reported, all right? So that's kind of cool. So we did a classic lab on that, the horsepower. Thank God we got that in before COVID time. It's a great one. All right, so that's kind of the introduction to energy, working power. And then we got to talk about